Hello, my name is Eloy Rodriguez, and we're going to go over this problem here. We'll do a little review over the volumes of a square and area of a square and volume of a cube. And we'll go over the circumference of a circle and the area of the circle and the volume of a right cylinder radius. Those are things we'll be reviewing to actually handle or solve this particular problem. We have a right cylinder of a radius 2 centimeters is going to be removed from a cube's whose edge lengths are 10 centimeters. What is the total surface area and the volume of the remaining solid? Meaning that once we remove the cylinder, how much surface area is left and what is the volume? In this particular case, we know that pi is an irrational number, meaning it's 3.1413 forever and ever. It's going back. And we're going to round pi to 3 just to make the calculations easier, all right? Okay, let's start with a little review. This program I'm using, by the way, is called SketchUp. It's a three-dimensional drafting thing that once published, you can actually look at it in all sorts of different perspectives, and it has virtual reality and augmented reality options as well. So I started here. So I'll move it and I'll say, look, I've constructed this square, you see? And it's 10 centimeters by 10 centimeters. Actually, I'm letting it represent this 1,000 millimeters, but we're scaling that to mean equal to 10 centimeters. And we can see then, if we wanted to talk about the area of that particular square, right, so that we can say that, well, simply that's going to be 10 times 10, but also multiplying centimeters times centimeters. So let's say that the surface of this one side, let me go back here. Yeah, so this, bear with me because the letters, I'm using my mouse. The surface of this one side, right, will be equal to the 10 times 10, or in other words, 100 centimeters squared. Because centimeters times centimeters means you have two copies of centimeters, which you can look at it as that, right? There we go. Beautiful. Now, if we make a 3D version of it, and we want to know the surface area of the total area, well, you could see, like, if a dice, how many sides does it have? Yeah, that's right. It's got 6. So if this is 1, and we multiply that 6, then we would expect, if I did the surface area of the whole cube, which I'll write it as surface area of the cube, let's just put a C here underneath, would be equal to 6 times, right, the 100 centimeters. I'll just put that times the 100 centimeters, squared. So we know at least we can solve the surface area of the whole cube is going to be this thing here, which is 600 centimeters cubed, squared. No, the distance, remember the perimeter, just the length, those are measured in centimeters, see it? But when you multiply them, you also have to multiply the units. So we get 600 centimeters squared. Any questions there? Nope. All right, that's good. Okay, so that's good enough. Now, let's use this property that's called extruding. That what we'll do is now convert this guy into a cube. And so what I'm going to do is use this key over here. It's called extruding. And then I will go here and pull it up. That's pretty cool. I'm going to pull that up until I hit 1,000 millimeters, which represents 10 centimeters. You can look at the lower right-hand corner as it's growing. By the way, this program is free to students. It's a great program to look. Now take a look at what I got here. A nice big, cube. And guess what? It's 10 by 10, correct? And it turns out that this also, the height that I went up is also 10. So I got 10, 10 centimeters here as a height. So now, if we talk about volume, right? Well, that looks like an 8. If we talk about volume, that's 10 centimeters. Okay, so guess what our volume is going to be? Well, let's write it here. The volume of the cube, I'll put a little C underneath to remind us of the cube. Oops, I don't look too good. Let me get it a little further away. The cube, yeah, will be equal to 10 centimeters times 10 centimeters, right? Which is a surface area times 10 centimeters. So 10 times 10 is 100 times 10 is 1,000. So we got 1,000 what? What are the units? We have centimeters times centimeters times centimeters. That is 1,000 cubic centimeters. In fact, it can fit 1,000 little 1 centimeter by 1 centimeter by 1 centimeter cubes would fill that up. So there we go. So that's going to be 10 times 10 times 10 is 1,000 centimeters, and that's going to be cubed. Yeah, and so I got to put a little 3 here. There we go. Look at that. Is that cool? Now we've already solved the total volume and the surface area. If you recall, the surface area, as we said, was 6 times 100. So, maybe I'll put it here. The surface area of the cube was 1 was 10 by 10 is 100, but there are 6 faces to the cube. So that's, remember, where we came up with the 600 centimeters. What? Not cubed. Oops. That looks pretty cool. That looks like, what? Urdu. Here we go. So we got 600 centimeters. Not cubed, but squared, because we're talking about surface area, right? Linear distance is just centimeters. Cool. So that reminds us, we got that down. Now let's talk about the circle. So let's review a circle. First of all, remember that the distance is centimeters, is the perimeter, is the distance walking around the edge. Well, a circle has an edge too. So let's go over here and take a look. Yep. So let's see here. Let me, this is already the answer. Let me get rid of that. Okay. So if we take any particular circle, and let's take a look at it, the distance from the center to the edge is called the radius. So we have a radius and a radius. If you add your two radiuses, you have 2 times r. We're by definition calling it a diameter. And it turns out a phenomenon occurs that if you take a string and cut it the distance of this diameter, or 2r, you can put it around the circle and it'll come all the way back. If you start here, you come all the way around it to here, almost by 3. So 3d, that's easy to remember, right? In other words, any circle, I don't care if it's a planetary and you take a circle out of the planet from North Pole to South Pole, you're going to see that the circumference, by the way, the squiggly line means, is approximately 3d. To get spot on, we have to change it so that it'll actually meet when it comes around. And we change the 3 to what's called pi. And pi is a little bit bigger than 3, 3.14113, and it goes forever and ever. It's a irrational number. Remember, in this problem, we're going to just call pi 3, but you should know it's not. And so, by the way, what is d? Well, d is equal to 2 times r. So if I plug it into d, I have pi is equal to 2r, and then I just distribute it around. So that's the famous circumference, or the distance around the circle, is equal to 2 pi r. What about our case? Well, we're doing an approximation because 2 is here, right? And we're approximating pi with 3. See it? So we have 2 times 3 times 2. So that it means the distance walking around will be 2 times 2 is 4 times 3 is 12 centimeter walk around this circle. That's if you were a little guy walking on this circle right here. And walk around like that, you're going to be walking for 12 centimeters. Because this radius, remember, as defined by the problem, is equal to 2. Right? And that's going to be 2, what? There's a 2 centimeters. There it is. See? And that's where this 2 is what I plugged into the radius here. So, and I let pi equal 3, so that's where we get 12 centimeters. Okay? Cool. Now, how would we get the area of that circle? Well, if we slice it up like a pizza, so, this is not, r is not 3 here, hold on. That says here, we know that in every case in this, since we've sliced up our pizza, that our radius will always be equal to, according to the problem, radius is going to be equal to, it's supposed to be an r. Oops. Let's go over here. Let me go back. Okay. So, and every one of these cross sections, r is equal to 2 centimeters. That is given with the problem. Oh, actually, I have it already written right there, right? You see it down here? Except that would be 2 centimeters. Don't want to lose your units. There we go. So look, I took this guy and I divided up into 8 slices of pizza. 1, 2, 3, 4, 5, 6, 7, 8. Then, look, I rearranged them so that the radius is 2, right? But I got 1, 2, 3, 4, 5, 6, 7, and 8. See, I lined them up. And if you'll notice, it's starting to look like a rectangle. And so if I keep slicing the pizza thinner and thinner and thinner and thinner and then stack them up this thing will look much like a rectangle. And we know how to find the area of a rectangle. It's the width times the length. Now, you'll find that mathematics, to be able to prove a point, is a lot like this. When you have something that's more complicated, we try to use simpler shapes to calculate, to be able to find out ways of using what we knew before or know before and find out the solution. So actually later on when you get to calculus, you'll see that they find areas under curves by having little summing up little rectangles, areas of rectangles under that curve. You'll learn that later. So if we want to get an approximation, you have to realize that if this is a pizza, the circumference, the distance that we calculated, if you remember right here at 12 centimeters, is really the crust, right? So the way I have it lined up, half the crust is up here, right? So it was 12 centimeters, you see it? So the crust must over here be, that is the distance from here to here, right, all the way over to here. Why, that must be equal to half of the circumference, or half of the crust. The crust was 12, so half here must be equal to 6 centimeters. See it? So one way of getting an idea of what the area of the circle is to just treat this like a rectangle. So we have 2 times, well, remember this distance is 6, right, which is pi, where you're letting that equal to 3, right, and r is equal to 2, so that's 6. And now we have this width times length, meaning that the area of this circle that we're using would be equal to 6. By the way, we have 6 and 2. Remember, this is 2 centimeters. So what we have is centimeters times 6 centimeters. So we ended up having 12. You see that? Centimeters what? That's right, squared. Then, okay, so that's good. So now we know that this guy here, the area of this circle here is 12. So now I'm going to make a cylinder by extruding that up 10 centimeters. So we're going to go back down like this. See that? I go back around, I change my angle, and now I'm going to extrude. So I take this button over here, and come over here, and then I'm going to extrude it. See it? And now if you look to the right, I'm going to go up 1,000 millimeters, standing for scale to 10 centimeters. So there, let me put it on there. Okay, oop, oh, how did that go down? Oh, I know, I put 100. So let me go back up. Okay, there, let's try it again. Okay, there we go. How's that? Is that neat? Look, I can look all around and go upside down, upside, inside out. I like it. So let's take a look at that. Now, maybe we could answer, what we have to do is figure out the volume of this first. So let's take a look at the volume of this thing. All right, let's try that. So before we found the volume of the cube and the surface area of the whole cube, now I'd like to find the volume now of this thing. Now keep in mind that the area of one of these, let's call them a cap. So this cap here has an area, as you can see over here. You see where we have the 12 centimeters, right? And there are two caps on there. So for now, we know that each one of those is 12, right? So let's take a look at the volume of this. So what would the volume be? Well, if you had one area, right, was 12 centimeters, and then we went up 10 centimeters. Do you recall? It's almost like if you had a seam on this cylinder and you go straight up, you see? Yeah, and guess what that is? Well, that we went up 10 centimeters. But one disc at the bottom, one cap, was 12 centimeters, right? So the volume of the cylinder is going to be equal to the volume, let's call cylinder, let's just call it CY, or CYL, like that, will be equal to the 12 centimeters, remember, of one cap, there you go, times the height that we went up. And that's, you know, the famous formula for a cylinder. So that's going to be 12 centimeters there, but then we multiplied times 10, but remember area is squared, and then we multiplied times 10 centimeters, see it? There you go. So now we know that the volume of the cylinder, this doesn't look good. I don't know how that, let me get rid of that. The volume of the cylinder. Oops. I do that every time. Okay. Is going to be equal to, and that doesn't look so good either. It's going to be equal to equal to 120 centimeters what? Well, we got 120 meters squared and another centimeter, right? Centimeter, its volume is going to be cubed. There you go. So we got that. And, well, the surface area might be a little more difficult to figure out because we're going to have to actually straighten that out. And I'll show you what I mean. But before I do that, I think we can answer a question now. We know what the total volume of the cube is, and we know what the total volume of the cylinder is, right? So we can calculate, once I put the cylinder in there and then subtract it from the volume, let's see what the remaining would be. So I could go here. Remember, this thing went up 10 centimeters, right? So I can, let me get rid of that. Oops. Don't want to do that. Okay. And then what I'm going to make it a group, so it kind of makes it into a kind of a single meter. Watch what I do now. I'm going to make a copy of this and drag it over. Look, and I'm going to come over here roughly about right here. Look at that. So now I put this cylinder in the cube. See it? Is that neat? Now what I'm going to do is make it so that I can now remove this, and then we'll see how much remaining volume there is. So what I'll do is I'll explode my little group I had there, and then do the old thing, and then I do this. It's called interface, intersected faces like that, right? Now I'm going to take away this. Look, wow, that's cool. You see what happened? Go all the way down here, and then I got that other lower cap. Then I'll get rid of it. See it? There you go. Look at that. You can actually get it set up so I can actually kind of go into it. Look, we could actually track through. Good for video games, huh? Okay, now the question is, how much volume do we have left? Well, we know what the volume of the cylinder was, 120, right? So, let's see if I can write it up here. Yeah. So the volume of the cylinder is 120. Let me write it up here a little bit different here. Let me get rid of this. Okay, and let me put a billboard here so it'll be a little more easy to read. A billboard would be just a rectangle, right? There we go. So now let's go over here and just write on there, surface here. So we're talking about the volume that we had calculated earlier was the 12 centimeters, see it down here, squared, plus the height of the 10 centimeters. So we know that the volume, right, of the cylinder, and I know it's using a C2, but remember this C over here is for the cube. So that's why I'm going to put a little letter under here that, oops, let me go here, and that'll be the cylinder. Okay, and I think you remember that we had 120. 120 centimeters squared. Cool. Well, that's easy enough. So now let's see what's the total remaining volume of this cube. Well, that would be the total what it was before we removed it. If you remember, the total was 10 times 10 times 10, which was 1,000, right? Cubic centimeters, right? For which we now removed the cylinder that we implanted in it. So that was 1,000 centimeters cubed. And by the way, this is volume, right? So it's cubed too, because it was 12 centimeters squared. That was the surface area of one cap. And then times 10. So that if we subtracted that, then that would be the 120. Right, so the first answer to the question would be, what is the total volume of this remaining volume of the cube once we remove the cylinder? So there's the cylinder, see, nice. And that's also cubed. So the answer would be, well, that's easy. It was 900, right, minus another 20. So we would be at 880 would be the answer. 880 what? Cubic centimeters. Right? Centimeters cubed. That was the easy part, I think. And there we go. Now, take a look about the surface area of this new creation. If you look at it, we've lost this cap here. And then if you look underneath it, right, well, we've lost that cap there. So we already know that one cap, as we talked about, was 12 centimeters, right? But be careful, because when we move that, look at that. When we move this, we actually added all of this surface area here onto the cube. So we're actually adding some surface area by removing that cylinder. You see that? That's tricky. So let's try that then. Let's talk about answering the second part. The second part is what surface area is left after. So first of all, how can we find the surface area of this cylinder? Well, recall, right, that this thing here was, if you remember, this part here going up was 10 centimeters. You see it? So we could do that to calculate volume, but now imagine that I unroll it like a roll of toilet paper or hand paper, right? So that I can figure out, I know that the distance going around here, the circumference, if you recall, remember, we had the circumference here that was right here, 12 centimeters. So if I go out 12 centimeters like this, suppose I wanted to unroll this thing. Let's unroll it. So I'm going to go out this way, 1200 or 1200 millimeters, which represents 12 centimeters, you see? And then I'll make a copy of this and bring it down to the base. And this would be the cylinder's skin on the edge, laid out as a rectangle. Look, I'll go right here. There you go. And then I'm going to connect this piece right here, right to here. And then we go to here. And then we go to here. There, look at that. That's cool. It looks like it's unrolling, right? See it? So let's find that. I'm saying that the side of the cylinder is equal to this sheet here. And what is this? Well, we already know that this guy's 10 centimeters. Oops, let me put it right here. See it? There's the 10. Oh, don't like that. Here's a 10 centimeters. And remember when the circumference? The circumference, if you remember, was 12 centimeters. And so this guy's going to be equal to 12 centimeters. There you go. That's neat. Huh? So what would the surface area of the side of that cylinder be? It'd simply be equal to, this side surface area would be equal to 120. Now that we're talking about area, it's centimeters squared. So there we go. There it is. Well, that's a while squared. E. I'll do it again. There you go. Okay, now be careful. So that means we've added in the inside of this thing here, in the inside, look, I'll put it like a line. I'll go like this to show you that the inside of this guy, look at that. I do like a little arrow here to show you the insides. Yeah, is 100. We've added 120 centimeters of area in the inside of this cube. But we have to subtract the two caps that we had. Well, the area of one of these caps, right? The area of the cap was simply going to be pi r squared. In other words, remember we had 2 pi r squared. So what was the area of just the cap? Well, it's going to be, I think we are right here that the area is pi r squared. So let's write it right here. Remember that the area was equal to, right, pi r squared. So, and where did we get it from? We got it from over here. All right, because we have radius, right, that's pi. So r times r is pi r squared. So let's just write it here. The area is pi r squared. But for our purposes, we're using 3, right, for the pi, and 2, right? So if 3 times 2 squared is 4, that's also 12 centimeters. And since we're talking is, right, is 12 centimeters squared. There you have it, right? Now what does that mean? Well, remember, we've lost the top and bottom of that. So if I want to know, talk about how much surface area there is, let's see what we got. And that finishes our problem, really. So what we have here was, when we're talking about the total remaining surface area, so let's write it like this. We have the surface area of the whole cube. I'll put it like, no, that doesn't look good. Let me go back. Okay, so the surface area of the whole cube, here we go. Yeah, and then we're going to have to subtract the caps. So the caps were minus 2 times the surface area of one cap, 2 times the surface area of a cap. That's like the top and bottom of the cylinder. Plus, we have to add in the area that we added by removing that cylinder in the center of the cube. If you recall that, that would be the surface of the side of the cylinder. So I'll put side of the cylinder. Right, and side of the cylinder. I'll just abbreviate. Okay, and that would give me my total surface area. So that we have the answer of 800 cubic centimeters of the volume after we removed the cylinder, but our surface area, the little trick here, remember we had 6 times 100. You see it right here? That was equal to 600. I got it right there. See it? So I have 600. And that's area, meaning centimeters squared. There it is. All right, minus 2 times, minus 2 times, it's like my mouse sticking. Okay, I'll try it this way, minus, yeah, now the 2 caps, remember 1 cap was equal to 12 centimeters squared. So that means the top and bottom that have disappeared now are equal to 24, right? That's a 24 centimeters squared. Yeah. Okay. And then we have over here plus what we added to the side cylinder. Remember, that's right here. Ooh, that's cool. Wow, what happened there? I took it from here and went oh well. Let me go here. Right here, it goes right there. It's not adding up. Oh well, forget it. That's where we're going. So that was going to be plus, yeah, plus 120 centimeters. So we'll go right here. Boop, boop, boop. Centimeters. Okay. And what does that equal to? Well, let's take the easy part. Well, if you take 600 and subtract 100 and then subtract 20, we'll be at 580, right? 580, and by the way, this was squared. Okay, and that's centimeter squared. And now we have yet to subtract the 24 centimeters. So if we take the 24 centimeters squared, see how you do it? And there you go. And so that's also squared. And what would that be equal to? Well, that's going to be equal, if we take 20 away from 80, we would be at 560, right? And then we have another 4 yet to take away. That's how I like to add and subtract in sort of like blocks. Makes life easier, I think. So if I take away 4 from there, you can see that we're going to have 556. So the answer would be the amount of area left in that cube after removing the cylinder will be 556 centimeters, and we're talking surface area. So that's it. Ta-da! What do you think? Is that cool? So the answer for the volume was 800 cubic centimeters, and the remaining would be that. Any questions? Well, just text me. All right. I'll talk to you later. Later on, I'll show you some of my designs that I built on this program. Okay, thanks.